I just wanted to say hello and thank you for coming to our CSI Greater St. Louis chapter November chapter meeting. It's great to see everybody here. I feel like every meeting we keep getting more and more members coming and showing their beautiful, lovely faces, and we love to see you guys. If any of you guys want to be more involved, we'd love to talk to you and get you involved to join a committee because we have some committee spaces available. And we're looking for people that's ready to get more involved and take a role and have some more ideas. So if anybody out there would like to, I do want to thank the people from KPFF for the presentation that they're going to present. I also, at this time, I'm going to bring up our food sponsors, Roofing Sales, and the new name Elevate also. So I'm going to bring them up here so they have a chance to talk about their company for a few minutes, and I'm going to pass it on to Kevin.
Hi, I'm Kevin Kyle. I'm with Roofing Sales Associates. We're a manufacturer's rep company in the area. We've been working with the Firestone Building Products line for 30 years plus, but there has been some recent changes, and I'm going to let Robert explain that. But as far as roofing sales, we can work with you in spec review, guide specs, paper roof insulation layout. We can even survey roofs if you'd like us to do general. Take a look at it. Here's what you might need and guide you along the way. So, but anyway, I want to thank everyone for coming. Really appreciate it. Looks like it'll be a good presentation tonight. I'm going to turn it over to Robert to say a few words about the name change.
Thank you, Kevin. So my name is Robert Anderson, and for 17 years I've been saying I'm Robert with Firestone, and I need to change that because I'm Robert Anderson with Elevate. Now, not the 30 plus years that Roofing Sales has, but I want to tell you a little bit about the name change just to make sure everyone is aware of it. Since the 80s, Firestone Building Products have been owned by Bridgestone, and last year Bridgestone divested themselves of the Firestone Building Products business. They want to focus on their mobility business, tires. And so they sold us to a company, Holcim, Holcim, which I hadn't heard of before. And they happen to be the world's largest building materials supplier, really big in concrete and aggregates, based in Switzerland. But they're really trying to grow here in the United States, and we're excited about the new corporate parent. They've really invested in us. We're building new plants and a new plant a year, expanding our metal operations. When Holcim bought Firestone Building Products, they bought everything: assets, liabilities, all the sub-brands, the Rubber Guard EPDM, the Red Shield warranty, the plants, the people. The only thing they couldn't buy is the name. Bridgestone wants to keep that Firestone name for their auto centers, and so we're rebranding. And so the Firestone roofing, wall, and lining systems that we're privileged to be in a number of your specifications for, those are now Elevate. So please, if you use SpecLink or MasterSpec to generate your specifications, those have already been updated to Elevate. But if you've got some master templates at your own firm, we'd ask you to please maybe review those and update those. If you need any help, certainly you can talk to Kevin or myself, but we'd be happy to assist with that. But basically, anywhere where there was Firestone, now there needs to be Elevate. So thank you for listening to that, and I'm looking forward to the presentation today. So I'll turn it back over to you.
Thank you, guys. Thank you, Kevin and Robert, for being our food sponsor this evening. Now we're going to keep it moving on to our presentation. So I'm going to bring up one of our favorite chapter members to introduce our speakers. And everybody knows them. We all know them. It's Mr. Steve Gantt.
I think we're talking about George.
No.
Yeah. We get you. Actually, the interesting thing is George is at home right now because I don't know if you guys have heard this thing called COVID. He's not sick, but he's exposed to this past weekend, so in order to keep everyone here safe, he stayed at home. He's going to do his presentation here. That's why Joe's wearing a mask. His whole family had son had last week. He tested negative today, but he's still wearing a mask. Just for you guys.
And the whole family tested negative. One guy who wanted more, but this is awesome. So I'm going to come over here and do my other duty and introduce George. George, you're going to do the prehistory, right?
I am, and I hope everyone can hear me.
You do that okay?
Yep.
All right, go for it.
Okay, that sounds good. My role this year is to talk about history of whatever topic that we're talking about. So there's a long history of making roof spaces nice and habitable for human beings. And going back in history, this is a fanciful artist rendering of the Hanging Gardens of Babylon. It's the only one of the 7 ancient wonders of the world that has not been definitively located. And that's why the question marks are up there by the date. Is it mythical? Was it built in Babylon but destroyed in the 1st century AD? Or was it built in Nineveh about 700 BC? Those questions are all sort of out there. The thing to keep in mind about this, and this will carry through, I think, my part and also pretty much the presentation, when you're building on a roof, when you're putting plants on a roof, when you're using the roof, you've got a couple things to consider. The structural element obviously is going to be very important, handling the weight of the soil, the plantings, handling the weight of people out there, whatever activity is going on and whatever's put on the roof. And in the particular case of a green roof, which this is probably the earliest example that you're going to find, how do you irrigate? How do you make green in a brown climate? This is Conwy Castle in northeast Wales, and it was built in the 13th century by Edward I. And it really illustrates the military adage of holding the high ground. And you've probably heard this phrase before. Holding the high ground, though, is not only because gravity is your friend to let you throw rocks and burning oil down on the bad guys, but most importantly, probably even more importantly than that advantage, is the ability to see what's coming. So this is a model that shows how the town and the castle looked. And you can see there that they're making maximum use of the visibility. You can peer out over the bay. You can look at the little river coming back there. You can see the grounds, coming in. And then if you look at the castle itself, you're not looking into a courtyard. You're really looking into flat roof spaces, which were used for support for whatever was going on the roof, looking out or fighting wars. So views are important. And we're going to look at another instance of a view in the 20th century. This is a map of the Philadelphia A's ballpark in about 1910. In the earliest part of the 20th century, they were a powerhouse. And they built a new ballpark. And you can see kind of to the right-hand side of the ballpark, there is a row of row houses. And that fence out in right field is only a 12-foot fence. 1913 World Series. People took advantage of their rooftops and the rooftop view to peer into the ballpark. And the best thing was that the tickets were free, at least probably in the first World Series, until people who owned or lived in the houses realized they could charge to let people on their roofs. And then they could sell hot dogs and beers and kind of do it all without having to pay the Philadelphia A's. So this was the World Series of 1913. Next slide shows what had happened by the World Series of 1929. At this World Series, 3,000 people per game packed this rooftop. So what happened was, you can see the outfield wall over to the left side of the screen there. By that time, the A's had gotten so upset, they decided in like 1930, and they built on top of their 12-foot brick wall another 28 feet of metal fence. At any rate, I guess the moral of this story is, if you have a roof with a view, you always have a view. Things can change. And this is possibly the world's largest green roof. This is Millennium Park up in Chicago. They claim it to be one of the largest extensive green roofs in the world. 25 acres. Now, if you've been up there, you say, well, how is this a roof? This is at street level, right? It's a roof because it spans over train tracks and it spans over rail yards. If you're planning your green roof, this might be the model that you want to put on the top of your 2-family flat. Pritzker Pavilion seats 4,000 and it has 7,000 for lawn seatings. There's various sculptures, fountains, play areas, and a skating rink, 11 separate venues total. And you can see it's quite extensively landscaped. But I think the thing that this has in common with the roofs that we're going to be talking about today, other than maybe scale, is that it is accessible, it's useful, and it is a delightful place to spend some time. So I'll turn it back to Steve or Joe.
So for myself personally, I've been in this industry for probably about 20 years out of college, and I used to do healthcare design. Actually, I used to work with George years ago over at Canton Design. But probably for the last 8 or 9 years, I've really switched over and really focused more on adaptive reuse. And with that being said, my co-presenter here, Sarah, I'll let you turn my phone.
Thanks, Joe. Hi, my name is Sarah Johnson Clark. I have been in the GIF for about 4 years now, for about 4 years. Well, Joe and Alan decided to take me under their wing, day one, and I've really taken an interest into adaptive reuse. So I've done a good handful of store renovations with Joe and Alan, and to do more. And we look forward to presenting about roof amenities today.
So you want a roof deck, green roof, or roof amenity. That's really what we're talking about, especially with regards to existing buildings and our local standard of care. So our agenda today is, it's a roof. What can we do? We have structural design challenges associated with using a roof for support of people and or vegetation. Structural solutions for repurposing existing roof, and also conclusions and questions. So this is intended for a general audience, so we're not going to get into every last little number. It's not like that.
What can we do with an existing roof? So first we're going to talk about exactly that. What can we do in terms of occupancy, but then also in terms of structural solutions for the roof amenity itself. So starting with the types of occupancy, the example that you see here in these photos is the 900 North Tucker building in North downtown St. Louis. This is considered a roof amenity that has 2 parts to it. As you can see, we have an enclosure, and we also have a lot of outdoor space. And this is actually a place of business and or event space for the building occupant, not necessarily a public event space, which for us structurally that is a very crucial number that we need to understand going forward. Another example that I think many of us are familiar with is having a rooftop bar or restaurant on top of an existing building or even a new building. So for example, in the photo on the left, you'll see the 360, which is downtown. I'm sure most of you know, you can't really miss it. And then another example is shown in the other 3 photos called the Angad Art Hotel. One critical thing about this one is in the top right photo, you will see that there was an existing penthouse. And then you'll also see that there is an expansion as part of our amenity space. But then you'll notice that it looks like it flows fairly well with one another. But then you also see the photo on the top center. That's from the ground, as you can tell.
Right, and for those that are unaware, the SHPO is State Historic Preservation Office. You're going to go in for national tax credits and even state level tax credits. You go through SHPO, your Part 1 and Part 2 application first, and then eventually works its way over to the National Park Service. Traditionally, Missouri SHPO is a little bit more cautious than the National Park Service does. So if it passes SHPO locally, you usually pass through the National Park Service. So in the lower left corner, this one alone, it's over downtown West area. It's an existing telephone exchange building in which the building itself had plenty of extra capacity. So we actually reanalyzed the building, did a little bit of supplemental support, and actually brought it into shipping in the pool. These pools prepackaged come around $40,000, and it's significantly less in cost versus having a custom pool added to a roof. So it's a good option as well. And then in the upper right corner, this is the last hotel project. We ended up designing basically a steel pool system to be brought up in two parts by lift and then welded in place. We had an entire new frame structure of it as well, with occupancy and existing building. And then finally, in the lower right corner, you're going to notice something that's really interesting. This is Hotel St. Louis, not to be confused with the last hotel. This one was actually originally built in the late 1890s and actually had greenhouses on top of the roof, as you see in the lower right corner. Well, since that time period, those greenhouses were actually removed probably before the 1920s, and everyone forgot about them, most people. So when it came around to repurposing this building, the discovery that greenhouses had once been there at one point in time, that allowed for a new replica greenhouse system, even though it's an enclosed structure and used for different purposes, to be built on top of the existing roof. Because at that point, SHPO would allow for this alteration with the guidelines accounted for, because it had been there at time of original construction. Okay. So additionally, we'll talk about blue roof and green roofs. So green roofs, this is an image from a project that our Portland, Oregon office did in downtown Oregon. And then the upper right corner would be a blue roof system. So blue roof systems are becoming a little bit more prevalent, not as much in St. Louis area, originated the concept in Manhattan or in Brooklyn while back. And the idea is that we have combined sewer systems such as St. Louis or other Midwest and East Coast municipalities, where we have peak storm surcharges, because the water from the roof systems and street level are actually entering into the sewer system combined, you end up with more water, more wastewater than what the system can handle. So what the blue roof system does is it allows the actual owner to have an automated system that stores water on the roof for maximum 48 hours to avoid mosquito larvae development. And then basically once your storm system is able to catch up, that's when the water is released from the roof back down into the sewer system. That way you're reducing some of the potential for water going into the riverways. So what's an interesting fact is the EPA states that 13.4 billion gallons of treated sewage is discharged into the St. Louis riverways each year because it's combined sewer system. So that's why there's such a sort of focus as this being an option for rooftop use as well in urban environment. All right, so now we know some things that we can do with the roofs. We'll just talk about what we can do with amenity structural systems. So sometimes we run into cases where you have, let's say, a heavy timber building, or something where the structure itself was really lightly designed in the first place. There's not a lot of extra capacity. So this is an example of 300 South Broadway, which is now repurposed or re-identified as ballpark house. I think it's what it's branded right now. It's right across from the stadium. What we ended up doing is putting a rooftop amenity, rooftop deck on top of the building. And what was really important was we're overloading the original structural capacity below. So to try to get the weight down to the swing rooftop amenity, we ended up actually going with a full form construction at the top, which ended up reducing the weight to only a quarter of what it would have been had on the traditional steel concrete system. So this allowed for strengthening the columns along the building and other aspects of really reducing costs and saving the owner quite a bit of money in the long run.
Another structural system that is often used is simply steel framing, whether this is using wide frame steel or in this particular case we used HSS or tubes for our beams and our columns. This particular system is beneficial, especially if you want glazing. So these photos here and the rendering, this is of the 900 North Tucker building, the first photos that I showed, which in those photos you could see that it was three-sided glazing, sorry. And so this structural steel framing allows for that. And then another thing, just based on the rendering, you'll see that we have steel amenity, and then we also have a pretty significant amount of steel strengthening, which we will discuss further later.
Sometimes, and quite often, to be honest, we'll end up running into 1920s era concrete constructed buildings. Okay? So if you're going to a rooftop amenity, you're going to want to have an interior space, especially for your vertical transportation and meeting area for building occupants. And then you're going to want to have your roof deck, which a lot of times is going to have this long paper system. So what that means is that your interior space is going to be higher than your exterior. So that way you can allow for your rigid insulation and your slope to be able to breathe the membrane. So if we're going to go ahead and raise the floor anyways, why not go ahead and use that raised floor in combination with the existing concrete structure below to strengthen it all? So what we're doing here in this particular example is we use geofoam infill aligned between original concrete beams below. So then we pour the floor deck on top, which you see in the light blue. And what that did, in a sense, was allow for the new floor system to be monolithic with the concrete beam below to basically double the beam depth. So this allowed for us to get the architectural elevation needed and also allowed for us to strengthen the floor system below without having to do any work on the underside. So it's sort of a win-win scenario. So if you're thinking, if you got a concrete building, you want to do a rooftop strengthening measure, you know you have to raise your floor system up, consider talking to your engineer record on this particular idea because it doesn't.
And the last material that we're going to talk about that many of us I'm sure are familiar with is using wood or composite deck systems. This particularly is just beneficial for whenever you do not have an enclosure or you have an open air system or you have an amenity space that may have an open structure such as a canopy or a pergola, something of that nature. One thing that we can do, which you'll see in the middle photo, is we can prepare your existing building to have a pergola, even if for example, budget does not allow a pergola immediately. We can plan for the future, like shown in that building. So now that we've talked about what we can do with the actual new roof amenities, now we're going to switch topics and talk about design challenges. And first, what we're going to talk about is clues that the existing building may be able to tell us whether it was actually designed to have a vertical expansion or not. So one very obvious existing building clue for us is if you happen to go on your roof and you see a bunch of protrusions that happen to a nice even grid, typically they're aligned with the columns below. That's because they likely are columns. These are stub columns. And then automatically tells us that your existing building was meant to have at least one more story in terms of vertical expansion, or even more, depending on the actual size of these stub columns. Another example is in the site. This is actually a photo of an actual expansion. The original building was built in 1818, and it was a heavy reinforcement building. But then we noticed that for some reason it changed from concrete to steel. And then we found literature and seeing photographs telling us that, hey, they actually did have another two-story vertical expansion using structural steel. This is a building that both Joe and I were involved with. Another potential building clue is it depends on what is actually creating your slope for your roof in terms of drainage. Is it the actual roof structure that's creating the slope, like the sketch in the bottom right? This will tell us that that's probably meant to be a roof. It's going to be pretty difficult to change that roof structure to be flat. But if you happen to go on a roof and it's an incredibly low slope or a flat roof, then this tells us that there is the potential that this roof could be designed as a floor. And then another way to tell whether you have a flat or sloped roof is if you happen to go up there, you see a bunch of funding in the insulation. So in that photo, in the middle, you'll kind of hard to see through the small photo, but there were several areas, in this case, of funding telling us that obviously the drainage isn't working, or you do not have a steep sloped building, so there's a pretty good chance that this building could be able to expand vertically.
This particular building is over Lockett Square, right at 10 corners of the park, and it used to be a religious school system. It's now basically a charter school system. But at the time of original construction, there's an advertisement from that particular religious organization identifying that's going to be a 3-story building. And then we found on site that it was actually only built as a 1-story. So this in itself gives us, hey, we better take a look and see if there's any other clues in the building if it's able to take vertical expansion easily. So when we looked over at the stair towers, we found that everything in the building is non-flexible construction, all concrete. And so you got the stair tower, you have the stair tower top of it, the roof. It's all just hastily built wood and built construction. You would not put wood into construction if they meant for that to be the permanent solution. So that in itself gave us the clues that this was also built for growth expansion. Another example would be the low building downtown. So this building, what you'll notice is there's an excessively tall elevator penthouse, about 7 stories tall, something tall for 5 stories building. It's much taller than the 1 story that you normally find, right? So you will also notice down in the drawings that say, okay, well, something's going on here. That some of it widened out in the original structural drawings. Instead of saying 12 floors, they widened out to 7 floors. So we start looking at the history of the building, and apparently a senior level executive at Illinois Terminal Railroad left the country with several $1 million in the 1940s to keep the ticket for their 30s. For construction, also they didn't have the money to supply. So basically, they stopped the development at 7th floor and widened out the original drawing state. This one was
Another potential building too is if you have to go up on your roof deck and it feels pretty solid, or on the underside you see a bare metal deck, and again you go up and it feels pretty solid. There's a pretty good chance that you may have a concrete on metal deck system, whether it's composite or not. That would be to be determined. But regardless, concrete on metal deck systems are significantly stronger than just a bare metal deck or a tin roof deck, telling us that there's actually a pretty good likelihood that at least the deck itself would be able to withstand the additional load, not necessarily the framing, but the deck, which is definitely important in our case.
So if you go into 1940s, 1960s schools, anywhere around town, anywhere in the East Coast, doesn't matter. Take out the ceiling. You're probably going to look out the ceiling. What's that fiber board? What's going on with that? For acoustical? No, it's the bridge and free system more likely. So basically what you got is you got the little barbell, kind of like railroad tracks running between the steel bar joists, right? Then you got the fiber board. You tore that fiber board off, and find, and oh, look, it's like drywall without the actual paper thing. Well, common practice at the time to keep the cost down was actually go up there and lay out some welded wire mesh and pour basically drywall on top of the roof to make that consistent. Couple problems with that. One is the manufacturers actually simply say avoid excessive moisture, avoid excessive humidity. Well, we all know how to run here in the summertime. They've already knocked that one off. And then another thing is avoid heavy loads. So all trades using the deck as a work platform should exercise caution not to exceed the capacity of the deck. So if we're going to try to put rooftop in, there are any kind of heavy loads, we're filing this up. And then finally, you'll notice in the right corner, the maximum loading that these systems can handle are 40 pounds per square foot. If you look at building code, look at the public occupancy for roof units, that's 100 pounds per square foot. That's 2.5 times what this is ever used before. So at the end of the day, you see this, try to avoid using roof systems at the outside of the roof.
Another potential building too, particularly for mass masonry construction, which is obviously very common around here, is if you happen to go up to whatever your tallest level is, or if you have access to the roof, go up and actually measure the parapet, see how thick it is. And then there are several historic references. In this case, this is the Kerry Nolan 7th edition, 1929. But even the St. Louis building codes at this time had similar language or similar tables. This literature has tables that will tell you exactly how big your wall needs to be based off of how tall your building is supposed to be. So if you happen to go up there and let's say it's supposed to only be 13 inches thick, but it happens to be 18 inches thick, perfect, you automatically know that this building was probably meant to keep going upwards with vertical expansion.
Some more clues when you're walking with the building owner. Beam size and beam spacing, real simple. So if you go to a typical floor, you look up, first of all, you look at the beam size, just measure one beam. And say, okay, well, for example, this is over here on the complex. But the beam size, 16 by 22 floor. And you go directly up underneath the roof around the perimeter of the program. And you'll notice that same beams spacing is actually a little bit shallower, looking by 18 in this case. So what that told us is that the flat roof system, even though it's pretty flat, is actually never designed for public occupancy on the floor, just in that comparison. Real simple, you won't do it. And then additionally, another product is the old warehouse, right across from our offices, we're working redevelopment. And so heavy timber construction, the floor roof system is your 2.5-inch thick hung roof that was pretty common for warehouses. It's the same for the roof and the floors. Okay, well, they're the same capacity. They're not. You'll notice that in the upper right corner floor, we have 2 beams per bay, and then the roof, the same exact roof decking, we only have 1 beam in the middle per bay. That simple conclusion told us right away, boom, this roof was not designed for the additional loads. It's one of the spend some money to straighten it.
Perfect. So to continue on design challenges, we're going to break it up into 2 categories, at least in terms of structural needs. The first category is gravity challenges. You know, when we say gravity, we mean static loads or vertical loads. So like people or tables, chairs, anything that's not going to be moving a whole lot, at least in terms of the direction. And then we're going to talk about lateral challenges, which just means more dynamic loading. We have a wind, we have an earthquakes. So starting with gravity challenges, one particular challenge is columns. As Joe mentioned previously, let's say you have an existing building that has heavy timber columns. Well, unfortunately, most of these heavy timber columns were pretty liberally designed and likely do not have any additional capacity. And then another potential issue is we all know that roofs leak over time. Whether you take all the precautions, eventually it will happen. Well, what happens whenever heavy timber columns are exposed to moisture over time? We all know that they rot. So there's a pretty good likelihood that we would have to help these columns out, even if you don't put a roof amenity to begin with, just to bring them to code, so to speak, just due to potential deterioration. Another potential issue with columns, if you look at the photo on the bottom right, with pipe columns, they have actually a very similar issue to the heavy timber. They were very locally designed and often do not have a lot of accessible capacity. And they're also not as easy to strengthen, obviously, because they're round. And then lastly, if you look in the bottom left, you'll see concrete columns. And typically when we see concrete, we think, oh, it's big, it's heavy, it's probably pretty strong. Depending on when your building was constructed, that could tell us a different story. It could be fairly lightly reinforced. So we all know reinforced concrete has concrete and steel. That's the 2 components. Well, there might not be as much steel inside whenever you compare it to today's standards. You could also have what we call a slender column, which really just means it's too skinny for how tall it is, which is not uncommon. Another issue is constructability. What happens if they didn't consolidate it properly? This just tells us that the strength of our actual concrete is not going to be uniform like it should be, at least in today's standards. And then lastly, depending on when your building was constructed, the concrete strength requirement itself could be significantly less than today's standards. So today's standards, the minimum is 4,000 pounds per cubic inch per square inch. So if you take a little 1x1 cube, that little 1x1 cube can hold 4,000 pounds. Well, 100 years ago, the requirement was 2,000. So that's a pretty significant difference, at least whenever you compare it to today's standards.
Wood floor joists and built with wood girders. When you go home, you're probably going to start with your basement after this one. So, as Sarah's mentioned, good water infiltration, that's no good for wood construction, especially if you have wood rafters coming into your brick bearing pockets right under your parapet. As we know, for thermal expansion contraction, that little joint where the parapet, membrane from the parapet, that flashing point, that's usually the weakest point. That's when the water starts coming in. So it's very common if you take out the seal and go to the building, first of all, just start getting screwed around, poking your joist right at the brick box, especially in your roof. That's where you're going to find that you already have a reduction in the spring. That's not right for it. Another thing is builder creativity in early construction. So in the lower left corner, basically, this is an example where the joists were designed wonderfully. They came over to the steel girder. Well, instead of actually putting basically a ledger or something else attached to the bolt, like a face mount hanger, the builder was creative and just simply notched the top of the joist. So we only have about 2 inches of joist support, and we started cracking over. So just look for builder creativity. You might need to start thinking back to itself. And then finally, built up wood girders, especially in the 1800s with construction. And say, oh, we got 4 or 5 plywood girders across. That's great, we're good. No, usually over creativity came into play. And they would put splices and start showing maybe 2 or 3 of those 4 or 5 wood joists have a splice right in the middle, nothing else. If you want the numbers of what's left, usually those things should have failed a long time ago. We just needed wood joist, but wood girders just kind of luckily was wrong anyway. So you shouldn't have put weight up there from day one, to be honest. All right. So wood going through definitely. So as mentioned, these old warehouses, a few things to look out for would be one we talked about earlier, the new spacing, those wood for. Another thing would be when you have a change of occupancy through the international existing building code, you might have a different hazard level. Okay? So change the hazard level, of course, run through code consultants, or whatever your output would be, right? And make sure you don't have a fire rating issue. If you do have a fire rating issue with the funds effects, you can always do a charter check. So basically, for 1 hour burn, you lose 1.5 inches of material. So you can talk to your engineer record to see if you still have the capacity to meet a 1 hour rating for that jurisdiction time with it. If you can justify a reduction of the remaining material to meet your 1 hour rating, you still have that beautifully exposed wood decking system. So this is well cited. And most authority jurisdictions are wood jurisdictions. Additionally, as mentioned earlier, on moisture, look for deterioration. A lot of times the deterioration of these decks, you're not going to see it from the bottom side, this is really bad. You have to actually remove the roof membrane where your condensation is getting cracked. So the top side of the roof is usually where you're going to see more deterioration. And it's very difficult to find out if they remove the roof. So always call contingency to comment.
Okay, so switching materials to concrete beams and slabs. So again, most of us, whenever we see concrete, we think it's big, we think it's heavy, we think it's probably going to be perfectly fine. In many cases, it is. But the reinforcement inside might be telling us a different story. So, for example, if you look at the sketches on the bottom, you have the one on the left and you have the one on the right. They look a little different based off of where the reinforcement is located. So the one on the right is the traditional way to lay out the reinforcement, the proper way to lay it out. But there are times where, let's say, the little seats that the reinforcement is sitting on decide to fall over, and our top reinforcement now becomes our bottom reinforcement, and there's nothing on the top. Unfortunately, that does happen, and this just tells us that the capacity that that floor was designed for is not going to be so. So that's where a structural engineer will have to go in and actually calculate what the capacity is based off of how it was constructed. Another example of a gravity challenge for us is the type of construction. So, for example, if you look at the photo on the top right, you'll see a lot of lines. This is what is called a four-way flat slab. If you can imagine, you probably understand why it's called a four-way. We have reinforcement in all 4 directions. We have the 2 orthogonal directions and then the 2 diagonal directions. As you can imagine, that's a lot of reinforcement. It got really claustrophobic. It was not very easy to construct. So there was always going to be potential issues just because of how condensed that reinforcement is. And then also just due to how the loads are distributed, this particular type of system, it decides to deflect a little bit more than more traditional systems, a 2-way system. And so even though your floor or your roof could be meeting capacity, you might actually be able to see the roof sagging, and even though it is at capacity, that typically doesn't make us feel very good, right?
All right, start with my favorite topic, chipcrete. I want to say this avoid. So Jeffrey Bruce mentioned earlier, we're at 40 PSF maximum viable capacity, and we can run up. So you know that means your joists, your columns, everything's going to be under design to start putting something up there. Additionally, if you were to take one of these cables and you were to lay out a large piece of drywall, would you want one of these legs pushing down on the drywall when you're in the job site? Probably not. You're going to expect that's going to start indenting and punch through. Similar concept for Jeffrey Bruce as well, trying to do basically paper systems. So if you have to do this, the owner of the building really is dead set on having a roof management. Just go ahead and post up a line over each of the original columns, and then do an elevated frame, and then just strengthen the column. That's going to be the quickest way to try to reduce the cost. It's steel bar joists. So very common construction, even under current day standards, albeit with the current COVID material acquisition issues, so it depends. But still, it's a very good product, very cost effective. Whenever you find an existing roof, you got your metal deck and just these steel bar joists. Especially in our area, you're likely to live at around 20 to 25 pounds per square foot. More than that. And so if you see this type of system with the little metal deck with top, know that you're going to be having to strengthen the bar joists and the actual columns and stuff. Now, since we are in an area where we do pay wages, fair wages for union labor in this area, that means that we're going to pay more for field labor. So in our market, instead of strengthening the steel bar joists and seeing that lower right corner, it's usually a little bit more cost effective just to supplement the steel bar joists with additional steel beams. So just remember that when you're going to supply or top your engineering. Now, if you're in an area where you have low field labor rate, right work areas, it might be worthwhile having a conversation on strengthening the bar joists and seeing that lower right corner. That means you're adding steel angles at each original angles and putting well under the bar to the top and bottom of the hinges. Once again, in the market, otherwise emphasis.
Great, and then our favorite garbage challenge, and one that's probably the most common, is just deterioration. So, for example, if you look at the photo on the bottom left, that is an existing steel beam that is holding an RTU frame onto the roof. As you can probably imagine, this steel beam was not very well protected at all. And you can definitely see what happened. It was exposed to weather for a significant amount of time. It allowed the water to just pond up on the top and bottom hinges, and it decided to deteriorate away to the point where I could actually stick my hand through the web where that area is where things kind of like see. So in this particular case, obviously we would advise to replace it. Don't try to fix it because again, it's not going to be the most cost effective in terms of field labor. So another example of deterioration is the top right. And whenever we think of reinforced concrete beams, we think big, heavy, we think strong. And again, many of the times it is. But if you happen to go into a basement or if you look at the underside of your roof, where you know there's been a significant amount of water infiltrating over time, there's a good chance that you're going to see concrete missing. Yeah, these are the concrete cover on the bottom of your beam. So this typically happens whenever obviously your beam is exposed to moisture, and then the water finds its way into your beam through microcracks to the point where it finds the steel reinforcement inside. Once it finds the steel, obviously that steel is going to start to deteriorate, it's going to rust. Those rust cracks are really going to turn and expand, but it has nowhere to go until that concrete decides to pop off. And then this is typically how it looks. So in this particular case, we would either have to strengthen it or supplement reinforcement in this case. So we've already talked about wood several times. We've talked about how water is not wood's best friend. But then another potential issue with wood is renovation over time. So for example, if you look in the photo in the middle, this is in a roof, part of a roof rafter. And at one point there was a new opening put in for whatever reason, we were not entirely sure at the time. But that particular roof rafter was strengthened where it was allowed to take that opening. So there's a nice crack that actually went to full depth, which tells me that that roof rafter is doing nothing at this Another potential issue with renovations is if you have, obviously with wood, you're gonna have your plumbing and you're going between your joists or underneath your joists, or they're gonna decide to notch your joists. And there's a pretty good chance that they're gonna notch where they're not supposed to, or they're gonna make the notch way too big to where you actually need to help the joist out. So that is the example of this bottom right photo is that notch is a little too big and it's in the wrong spot. So this joist would likely need to be sistered or supplemented.
So we're just going to go briefly into the side of the topic, just so we all have a better understanding of how it is and what's focused on. So in general, if you have to boil it all down to engineer, there's other factors in play. But the main key is to do the second law. Why horizontal force inside the event is simply your acceleration times your mass. Right? So the way we work with it, once again, there's other factors as well, but that's the main key. So what's interesting is if you look at the lower left map, you look at a very strange place in the West. Missouri itself, you go from very little size of building over to Kansas City, which is only about 10% of the acceleration gravity. So if you drop the ball, that ball in Kansas City is going to go only 10% acceleration versus just normal rate. Now, if you go over to St. Louis, that actually increased 5 times. So basically, we're about half of what gravity is in terms of acceleration in St. Louis. Let's go down to Google, down in basically Nevada. Also, we go from percentage gravity to 40 times. So it's insane. We're about 3 times acceleration gravity. So you have to actually take things where you're dropping, you have to throw it. It's happening down in Bonterre, or sorry, not Bonterre, down in Manhattan. So let's see, we're in a very weird state. So that being said, we have different design effects in different parts of the state as a result of this. Because we never see those. So we have to really start taking a look from an international system building standpoint. What did they actually design to? And how does seismic pop come into play? So it's a little lollipop, showing kind of Kansas City, lollipop shaking just a little bit, St. Louis shaking quite a bit more. So we have different standards of care for each part of the state. For sure. All right, to build upon that. So if we do some quick little comparison, so older building codes say just take 20 tons per square foot of wind load, and that's what you're designing to build to. So that's what we see on the right side of the green space there. And that's pretty consistent in the Midwest at that time period. So this particular building over the hill, that would create a total wind pressure on the side of the building, create about 25,000 wind force. Okay. Now we take a look at Kansas City, probably a very low side in the economic deficit. So we take the size of acceleration in Kansas City, multiply by the building weight, and the ceiling balloon comes out about 14,000 pounds. So less than wind. So you can add a little bit of additional mass to the rooftop in Kansas City, and you're still going to be less total load on the building than just what is probably going to per foot wind. So not a big deal in that market. If you lose on the we take that in the same exact building, we shake it up to what we're supposed to do locally. We're at red, 59,700 pounds spatial seismic compared to 25,000. So that means that if we were to take a look at seismic loading on that building in today's market, in our market here, under seismic event, that building was 2.5 times the amount of load that is ever designed for the purpose of wind. So we're kind of looking at the terms here. So if you start adding additional weight, different things, different mass to the building, and the building didn't work in the first place, what do we do about that? That's a can of worms, and that's really what we're focusing on. Sorry. All right, so we know we got a little issue. We'll deal with it later on the side of the topic for our market, but you can't see it not a big deal with engineers. So for here, we're also going to talk about wind. It's kind of the opposite. So what we did was we actually demonstrated in that right-hand corner what the different coding time period for our local market was. In 1917, they said, if you put 30 feet of stuff on a tall building, that's what we're designed for. By 1930, they lowered it to 20 feet of stuff on the first 100 feet and 30 more. Then as you see, keeps going. So basically, now the current day code, the same building, you're redesigning the building to 16 tons per square foot window versus 30 back in 1817. So for wind design, we've actually liberalized quite a bit from what the codes used to be. So we're kind of going the opposite direction. So if you're actually going to handle wind sales with all building in our market, chances are we're far over zoning that old building in the first place versus what that means they will do. So it's not a big deal. So really for us, it's more of a focus on adding extra weight to them because that's the side issue.
Another lateral challenge is understanding the standard of care at the time your building was constructed. So, as it's mentioned, not all buildings actually have a lateral force resisting system. There's a pretty good chance that it's not. But at least for taller buildings, there is a chance that there is something. And so it is always good to understand the standard of care at the time. And many times the standard of care is dependent on your height of the building, as well as your proportions of your building, your width and your depth, and how it actually relates to that height. So for example, in the photo on the right, this is a plan of a building. You'll notice that it is a really long, skinny building in one direction and then incredibly deep in the other direction. So the green that is highlighted in the right left direction, that is actually our lateral force resisting systems. And then in the up-down direction, you'll notice that there's none. And that is just due to the proportions of the building and how it actually relates to the height.
Thank you. So we're going to get into the gray area of the code, which, as we all know, unedited this, right? So the International Existing Building Code says basically if you're going to change anything about the building, you need to analyze it. As we demonstrated earlier, if you start bringing size and top into play in our region, just tear down the building because it's all going to fail in the first place, right? Well, the IEBC recognized that's not realistic. We need to actually try to preserve and sort of do a do no harm approach. The IEBC built in this little exception. And what it says, as long as you're not increasing stress in the building's lateral system, shear wall will keep it stable. If you're not increasing the stress by more than 2% from the pre-alter state, your grandfather then don't do it, you're fine. And that's the key. So depending on the authority of jurisdiction that you're working with, some authority of jurisdiction will accept supplemental lateral resisting elements. So what that means is if the authority of jurisdiction accepts this ruling, you have to talk about it, which the St. Louis generally does accept it. That means that if you put supplemental shear walls or other elements that are helping the building, but not really bringing up to the word rainy building, you're shedding some of that load off the lateral system to keep the original system. City of St. Louis generally accepts that interpretation. So just talk to the HJ you're working with and make sure they're on the same board that was copacetic with the standard of care. So for local environments, instead of doing a full lateral upgrade for a 10-story building that's probably going to easily be around $3 to $5 million a lot of times, we'll look at actually converting, working a small redefinite. We'll actually look at converting some of your walls into a low-fly shear wall by adding thin lightweight metal to metal shear walls just to keep the cost down. And due to financial constraints, especially in our environment, a lot of times this is accepted. So you've heard of some probably one of people's whole ductility and non-ductile topic. So when you're designing a building, you want some highly ductile. So what does that mean? So you're putting reinforced masonry, right? Anything runs wants to water around. That's considered non-ductile. That means that when you're placing pressure, you're trying to shake that building back and forth, right? You're hardly lose it off until it's overloaded. Then all of a sudden it snaps and collapses, right? It's like a saltine cracker. You start twisting and pulling a cracker, so you push the part and all of a sudden the part is right? But then you take that last happy, you start pulling on it, you'll then nothing changes, right? It goes back to a little shape. And you pull it hardly. You bring the product back into a ductile state. It stretches. And it still stands up enough to not snap enough to get out of it. You have to have a new scientific design. So if you're going to use basically a mono frame, something to seal it, that's considered highly ductile. That's the goal for a lot of practice structural engineers whenever they're trying to bring building up code or trying to do system.
Another potential lateral challenge is the type of construction, particularly for steel frame buildings. Nowadays, whenever we have a new steel frame building, as Joe mentioned, this term moment frame That, whenever we say moment frame, you can imagine a column and a beam coming together, and then let's say we start trying to push it. Well, that column and beam originally started with a 90-degree angle at that connection, right? Well, whenever it starts moving, that 90 degree stays there. So that means that it's able to move because your columns and your beams are what is deflecting. And so that is what we call a fully rigid connection, which is very common for new construction or concrete practices. Now, depending on the area of your building, you may go into the building and you see what we call wind clips. That really just means that there's an angle top to bottom or an angle top seat at the bottom. And one thing about these connections is that they are not considered to be fully restrained. They're only partially restrained. So let's say a lateral event were to occur, that 90 degree at that corner is likely going to change. And in most cases, in the KC region, that's going to be fine. These particular connections are actually pretty good in terms of resisting wind load, because wind typically goes in one direction. Wind is not typically hitting your building right, left. But then, as you can imagine with an earthquake, that's the opposite, where we're going to have your building going in multiple directions. And in this particular case, these connections do not like that. And so there's a likelihood that this connection is going to need some help if you have a great building.
Concrete moment frames. Okay, so if you go into an old building, for example, this is over there, for example, and you were to slice that beam, concrete beam down the middle, okay, you're going to notice that the top reinforcing goes over the column. It extends both directions pretty far, but the bottom reinforcing only goes in the column maybe about 6 inches, and the same on the other side. So whenever you start shaking the building, the top reinforcing is wonderful. It's exactly what we want to do nowadays, right? But the bottom reinforcing causes hardly overlap. Your cementation base, the glue that's in the concrete, only 6 inches, it's going to tear apart to be overloaded. So really, that bottom part is the weak part. It's going to get over and over. So that's something we talk about a little bit. All right. Additionally, again, real long, skinny buildings, that parts you are a little more skinny, whatever. You're going to notice that there was a big move for developers to go ahead and knock out all your interior walls and make them open floor, right? Real big push, right? Well, the problem is you have existing long doors that run facing perpendicular, doors that run long with your long wall. So to get rid of the interior walls, you start shaking the building. That means the board has to expand even further horizontally to get to your end walls. So by doing so, really, when you are blowing out those interior walls, you're making the building weaker and making it spiral. And so try to keep those interior walls. Now, if you have to blow them out and you have to do some kind of floor system work anyways, instead of putting plywood sheathing over the top of your wood floors, shoot that down. That's going to strengthen that horizontal ability quite a bit. Give you a better chance to keep the building standing and comfortable with the loads all the way back to the front of that wall.
Okay, so this is just a very, very brief example of that 10% rule that Joe was talking about earlier. So let's say we have a nice heavy masonry wall, which again is going to be very common in this region. Let's say it's about 50 feet long, it's nice, solid, there's no openings in it, which actually for us is great. But due to potential alterations, let's say you need to put a couple of doors and windows here and there, and let's say you end up taking out about 10 feet. Well, 10 feet of your 50 feet, that is 20% of your wall, which is over that 10% threshold. And so there's really two things that we can do. As Joe mentioned earlier, we obviously as a principal likely need to supplement, and then we will supplement it either by designing the new wall, whatever it is, your concrete shear wall, a new masonry wall, your light gauge wall, whatever it is. We will design it to take that 20% that was lost, or we will design it to where your what's left of your existing masonry building will only be exceeding the capacity ratio by 10%. So again, this is where you need to talk to your AHJ and see which way that they would prefer. Great. So now we finally wrapped up solutions, or we wrapped up challenges. Now we're going to be talking about solutions, both in terms of gravity and lateral. And I apologize if I should do really run through this fairly quickly, so bear with us. So for gravity solutions, we're going to talk about framing, strengthening. So whenever we say the word framing, we mean your roof framing, so your beams, your girders. I'll talk about your columns at this particular point. One very easy gravity solution is what we call steel scabs, which really just means we're going to be making whatever your existing steel member is, let's say it's a right plane beam of some sort, we're just going to be making it bigger. And there's a few ways that we can do that. We can add plate on the bottom, add a channel on the bottom, or in this case, this particular detail is from the 900 type of building that we have talked about a couple of times. The roof needed a lot of help, to where we actually ended up adding new wide range beams to the underside, essentially doubling up what our beams and girders were. So this is just one fairly straightforward gravity solution. And this is a photo. Sorry about all the fire protection, but you can kind of get the gist of, we have our existing steel beams on top, and then you'll see the new sections on the other side, deepening those sections. And this was all over basically like 80% of the roof due to the size of the amenity space. Another framing strengthening system is what we call supplemental steel. So typically whenever we add supplemental steel, as Joe has mentioned previously, we're really just trying to cut the span down of whatever your original existing roof is. We're either trying to cut your roof deck down, or in this particular case, we're actually trying to cut the span of your floor joist down. So for example, this is the 300 South Broadway project that Joe mentioned previously. The existing construction, we have our wood joists, and they ran, I think, about 20-ish feet, plus or minus. And instead of adding something joist, let's say we can double up the joist, that wasn't really reasonable due to constructability issues. One thing that we could do is add a new support line right down the middle. So now those joists are only going 10 feet, they're no longer going 20 feet, which significantly increases our capacity in general. So here's just a photo of what that supplemental steel framing looks like. Going right down the middle of our joist that you can see running right left. And then concrete framing. Again, whenever we say framing, we're just talking about our beams and our girders. We're not talking about our columns just yet. But with concrete framing, we can also use a very similar approach to steel, and that is by adding supplemental framing. In this case, that is adding supplemental steel framing. This is particularly good whenever the beam is either too damaged or it's going to be too expensive to repair your reinforced concrete beam, or in this particular case, the beam's in our way. So, for example, this is the 100 Broadway building right downtown. This is actually an access to the garage down below grade. And obviously we had the green beam that you see highlighted, that was our existing beam, and you can probably see that there is now a stair running straight through it. And this was just due to reconfiguring the stair. And our concrete beam's in the way. So what do? We add a new steel beam on the underside. We designed to support that existing concrete beam, and then everything that guy was holding, and we call it a day. So it's a fairly straightforward solution. And here's a photo of that.
So if you do have high constraints, there's ceiling, amenity, whatever else, so the way to strengthen is using fiber reinforced polymer. It's basically carbon fibers, so you can slot existing concrete between topside and epoxy in this FRP bar from the top. You can also use it to wrap around the beam as well as constraint for shear and fletcher. It's a little bit more costly to read because it's not used as often as West Coast markets. It is an option, and using pictures taken from some FRP we did already this Missouri moment. So additionally, if you have a concrete column that's really undersized for building up on a building, another thing you do is just drill it down some epoxy bars will focus around the perimeter, then just do reinforced gauge around, and then just pump in a high pump. That's an example of a 21C project downtown Boise.
So sticking with our concrete columns, let's say you don't need as much help, so you don't need, so concrete actual wraps is probably not warranted. One thing that you can do is basically make it a composite system using a steel strong back. You can see that in the photo on the right. You'll see that there is a new steel tube beam, which is actually anchored to an existing concrete column. And this was in this case, it was added because the new roof amenity load that we were adding on top was actually changing how it was applied to the column. So it wasn't necessarily that the column was being significantly overloaded, it was just because we changed how we were applying the load. Our concrete column did not like doing that. And then also, since we're in this particular case, we're on the perimeter of the building, well, what happens if you needed to make that column bigger? You probably don't want to get rid of your infill masonry that you see on the right and left. So in this particular case, to help with constructability, that's another purpose of this steel strong back. You're just strengthening the side that is actually accessible at the time. So now switching to steel columns, one thing that we can do is very similar to what we talked about previously, the steel scabs, making the section bigger. Well, we can do that with columns too. So in this particular example, we had existing wide plate columns, and again, we really needed to help them out. So all that we had to do was add channels on either side, and overall, we made the entire column section a lot bigger. We can do this with channels or plates, just depending on what you need. So now switching to timber columns, as we mentioned previously. Timber is often very difficultly designed, usually needs some help. There's a couple ways that we can do this. You could potentially, if it just needs a little bit of help, you could just add more wood, you can add more plies and make the entire wood section bigger. Or you can make it a composite section with steel channels and sandwich them on either side of the timber column and really help that column system out.
All right, foundations. So a long time ago in our region and other parts of the country, the whole thing of safety factor didn't really exist for geotechnical design. So the city of St. Louis, for example, stated that if you had a natural clay soil designed for 5,000 PSF capacity, like what does that mean? If you look at the current code for IBC, they said 5,000 PSF, they should say you're only supposed to be about 1,500 PSF. And honestly, if you get a geotechnical report, you're lucky to get anything much more than 2,000, even 3,000 sometimes. So what that means, before we do anything on the building, if you were actually to analyze that building without touching it under current codes, that thing should have sank and built a long time ago. That's the reality of how it goes. So all of a sudden, we're dumping a bunch of extra load on the roof, we're adding roof amenity, and the building didn't work in the first place. What do we do about it? So something you can talk about with your engineer records or your own project is say, hey, should we consider contacting a geotechnical engineer and see if they would actually give us an estimated soil settlement analysis instead of a capacity recommendation? So if you can go ahead and find out, okay, I want to add so much extra load to the roof, how much more is the building going to settle? That's more important than knowing it doesn't work in the first place, right? So if you can find that someone wants to settle maybe an extra inch from what's already settled, maybe the building owners will accept that risk. Just as long as it's in writing and you get the notification clause stating that you're not at risk as basically the design team. If they're willing to accept the owner, willing to accept that risk, you have to give them the owner. I'm not talking about the builder. And sometimes people are willing, because you start looking at $1 million worth of foundation enhancement and the project's over budget, that doesn't come up quite often, which is quite frank. Now, if you're talking about more than maybe one inch settlement, most practicing engineers in our region will say, no, I don't want to take that risk. I don't want to take that risk. So at that point, we'll start looking at other micropound options, right? So if you're looking at basically it's really far down to bedrock, and you're only adding maybe an additional floor to the building, maybe it's 1, 3, 4 story building, you might want to look at it a little bit. It basically looks like a corkscrew. You're going to go down the site, screw it into the ground, and then attach it to your system. It's pretty economical. A lot of times they're around 2,500 to 3,500 per building here. So if you don't have too many foundations, it's not a bad approach. Now, if you have significant loads, then you might want to look at an actual house where they're actually pushing steel pipe system down to bedrock. And then basically you're going to really get additional capacity. We're currently added 5-story buildings, and it's the 2-story building near downtown right now. And the micropower is what we had to do in the project.
Okay, now we're switching to lateral solutions. So again, lateral, we're talking about dynamic loading, we're talking about wind and our seismic. So potential lateral solutions for your existing building are as follows. First, we're going to talk about concrete shear walls. So again, whenever we think of concrete, we think of big, we think of stiff, and in this case, you're definitely right. Concrete shear walls, one major approach to them is they are typically incredibly strong in a very stiff system. This particularly is important whenever you don't want your building to move a whole lot due to brittle finishes. Let's say you have masonry facade, or you have infill masonry, so you have a multi-wide infill masonry at your building facade. And just to keep that brittle material from potentially cracking over time, you're going to probably add a stiffer concrete shear wall. Another particular pro is there is a pretty decent amount of field flexibility, because nothing is ever going to actually go as smoothly as you want on site. Let's say you're putting in your reinforcement and you're starting to work the building more than helping in. Well, there's a pretty good chance that you can just shimmy your reinforcement around and it will eventually work out. But the major con with this, due to all the field labor, all the reinforcement, all the formwork that is required, it is going to be very costly in terms of labor, even though it is a very strong system.
So if you have an existing building that has a frame structure all the way around, so really after around the depending on, you might start seeing that. If it's 1890s, forget about this. So if you have a frame structure where you don't have a low bearing reinforcement wall on the perimeter, you might consider putting moment frames to supplement if you're putting roofing on the top. This allows for the open programming still. Architects love this. And basically it's fairly easy to install compared to some other systems. But if you have a low bearing brick wall, real big brick wall around the perimeter, this is not the system for you, because what happens is it's too flexible. So the brick's going to suck up all the load due to stiffness, and that's going to fail for cracking, breaking apart before there's no frame wall should cracking. So only do some frame buildings.
So similarly with stone frames, another option is steel brace frames. Steel brace frames are typically stronger, they're stiffer than when compared to moment frames, but they are still considered very highly ductile system. That ductile topic that Joe talked about previously, that I was happy, which is very good for seismic loading. Another pro or con is that they can be aesthetically pleasing, and then there is some flexibility with the actual braces themselves. We can accommodate windows, we can accommodate doors, typically, or the entire configuration can be updated from the example that you see here. The major con is that it is pretty costly to install. As you can imagine, field flexibility is not as forgiving in this particular case, and then a lot of field measurements are required, and also just flexibility when actually installing, because again, you can take all the measurements you want in the world, it's never going to go up exactly how you want it to. So another example of a lateral solution, this is one that Joe did mention previously, is the light gauge steel plate shear walls. Mouthful. Essentially, what we will do is we'll take out as many partitions in the existing building as we need, and the ones that are remaining, or even the new partitions that are coming into play, and we'll simply add a very thin steel sheet to it. It actually will be so thin that you won't even notice that it's in your assembly, but it will be helping us out constantly. So another pro to this is that it is incredibly lightweight. The partitions are already there, or they're already going to be there. It's non-compressible, and it's also very cost effective. Again, partitions are there, and the steel sheet is fairly easy to install. Another pro or con, if you look at it, is It's not a super stiff system whenever you compare it to the steel motion or the concrete shear wall that we talked about. And so typically these are mostly beneficial whenever we're just over that 10% threshold that we were talking about previously. So that's the main con to them, is that they are not nearly as stiff as some other systems. So this is an example of what that shear steel plate shear wall looks like while being installed. Again, it's fairly easy to install whenever you compare it to other flight gauge systems.
So steel plate shear walls, just kind of below that. You imagine you take a soda can, you cut it in half, lay it out flat. It's pretty similar to that thickness, to put in perspective. So you can handle that between your drywall and your studs and whatever you most. All right. So again, if you got, let's say, long buildings that you are real thin, and you want to really try to cheaply strengthen it laterally, just take out your old drywall or old plaster and just put a plywood sheet with some plywood. It's really cheap to do, and you really stiffen up that system and give some flexibility to it. All right, so if you're doing let's say those steel or those something similar to the steel plate shear wall, if you get the pushback from a plumber, the electrician, say, hey, I can't get all the stuff in here to smell away. Well, then we can also get scrap race walls. Well, I should note that these scrap race walls, they're not exactly constant. So you have to get a little bit before it starts really coming into gauge. So if you're going to put some stiff brick building, probably build the system. FRP, mentioned earlier, by reinforced polymer, not as common on here, still do it. Basically, you can go ahead if you're putting a hole for existing brick wall, sheet applied there, you can wrap joints, but you know what? Please do not do the exterior application of FRP on your walls, walls. In our local environment, you don't have to repoint that wall probably every 40 years or so. And it's got the sheathing or the face of it, already of the repoint. It's non-reversible. So there's plenty of examples out there of doing exterior strengthening reinforcement walls. Just don't do that left image.
Another example is what we call shotcrete shear walls. So previously we talked about concrete shear walls. Well, this is basically the same thing, but instead of using concrete, you're using shotcrete, which just means that you're not going to be having all the cost of the formwork that's required for concrete shear walls. So in this particular example, you can see the reinforcement there in the middle, and then on the left, you can see the shotcrete being applied. And as you can probably tell in the image, it doesn't really look very pretty. There's going to be texture to it. There's going to be honeycombing to it. So typically with shotcrete shear walls, you're probably going to want to cover it up anyway, which is okay. You still get the stiffness of a concrete shear wall. It's just not as clean looking.
So if you have, let's say, a 3-story school building, you want to strengthen it, a good option would be to go ahead and build it a CMU shear wall. So what this will allow you to do is you build a block with your mason, right? And you pour out some holes in your floor above. In those holes, you find your reload through and then pump and flow out from the top side. So there's an easy application. So if you have a sort of 3-story less building, this is a good economical option if you have to go that way. Then finally, as mentioned before, if you have a real long thin building, this wood construction, consider putting plywood overlay on the roof system. At least that's really going to stiffen it up and help it back to those far away walls. Then finally, if you have an existing storefront building that's really wide but not deep, a simple way to actually try to straighten it, because what's going to happen is those old straight doors, it's really going to cause a storefront to actually start to bubble right at the front, right at the stem jams. So a real simple way of improving that floor is to make it more rigid. And you can do that by doing a thin concrete overlay with reinforcement or plywood sheeting overlay. So you see the lower left corner, that was some fine model showing that middle rocking failing. You know, the image on the right side is where we stiffened up that floor system. So the horizontal loading has the load by the clock, basically to all 3 long walls. And all of a sudden we've got quite a bit more stability. And the International System Building Code actually gives specific recommendations for what this is demonstrating. So it is code of. That being said, we got through it. So let's see during historic architecture from above the structural liveness. And at this point, so we're glad to answer the questions with him.
Anyone? We check online. Nothing online. So George mentioned at the beginning of the program, he did a little history thing. What we're trying to do this year with our programs is do a little bit of spec information for you as well, so you can tie this information back in when you get back to your practices and whatnot. So what I want to talk about a little bit is cross-referencing specifications. And one of the country's leading spec writers, Bob Johnson, had a few quotes here. Coordination of work is not our responsibility, but it's the duty of the contractor. So the contractor has to make sure all the parts fit together. We want to limit cross-referencing to the specific information that the person reading the spec might reasonably expect to find in this section, but it's actually somewhere else. What's basically, we want to say it once and we want to say it in the right place. That's CSI principle there. And then cross-reference to coordinated assemblies or systems whose components span multiple sections. Basically, we're going to get into a couple of examples here. So coordinating a roof deck, wood roof deck that's going to be occupied. We've got our structural engineer, KPFF, on duty here. We have our architect and probably a roof consultant going to be involved here. What elements are we talking about? We're going to talk structural framing, connections, decking, make sure it's all will stand up to everything they talk about. We're going to talk about railings, trims, finishes, and then we're going to talk about tie-in and penetrations to the roofing system because it's not just going to magically flow up there. So what sections could we infer that we're going to use here? Pretty simple, wood, so we're going to use rough carpentry probably. Probably wood decking, going to need some stairs to get up there maybe, railings, composite decking. But you're also going to need to cross-reference and mention waterproofing, traffic coatings, and possibly membrane roofing, depending on what we're getting into. Green roof, similar. We're going to consult the same people, but we're going to add in maybe a roof consultant, mechanical engineer. If we have a green roof, we're going to water the plants. We want to make sure that excess water gets off the roof in a proper way. Architect for sure, maybe a landscape architect, depending on what it is. What elements do we need to coordinate? The green roof system. Is it extensive or intensive? Is it trays or something else? What kind of plantings are we going to do? Are we going to have small little sedums or are we going to have trees? We have bulk soil up there. We have to do anything with the soil. These guys need to know what they're dealing with weight-wise as far as how deep it is. And then are you going to irrigate it? Or is it going to be just dependent upon rainwater? And then what additional supporting structures will you need? Specific sections we're going to need 3, concrete probably, a little bit of steel, some wood, 5 and 6, and then 7. Waterproofing, membrane roofing, vegetated roof systems, maybe leak detection. If you've got an extensive roof up there, you're going to want to know where the leak is so you don't have to dig everything up. And then your planting and landscaping information. And then my final slide, how do we coordinate awnings and coverings? Similar, adding those canopies onto the roofs, structural engineer, the manufacturer of that component. If it's a freestanding wind sail, you want to talk to that manufacturer to make sure you get their loading and their information gives the structural engineer. Talk to the architect, landscape architect. Finally, you want to tie in the roof penetrations. The elements that we're really worried about is tying into that roof, how we're penetrating that membrane or that roofing or the waterproofing. And then what's the covers look like? What are the sun control devices or whatever else we're putting in. So with that, I want to thank you for attending the program tonight. And thanks again for Roofing Sales for sponsoring tonight's meal. It was very good. Thanks for presenting.